Yeah, so the first part, it's asking for the surface charge density on each one. Yeah. The one on the inside is solid, and it has Q, and the one on the outside is a shell, and it has no net charge. Yeah. Um, but they're both metals, so that means they're both conductors. Mm. Which means on the surface of the first shell, surface charge density is just total charge uh, divided by the area, assuming that it's uniform. Uh, or you could just say Q is equal to sigma dA. And assuming that this is a uniform surface charge density, you are left with dA being the area of the sphere, which is 4 pi a squared equals Q, which makes sigma A equals Q over 4 pi a squared. No? Huh? Frozen? Mm. Oh, I wrote, yeah. I wrote the answer for part A. Q over 4 pi a squared. Yeah, because if this is a conductor, that means uh, if I were to take a Gaussian surface here in the middle shell of my surface, I should be able to if I, let me just do this correctly. So if I were to take a Gaussian surface here in the red region, I know that in the red region has to be E has to be 0 because it's a conductor. And from Gauss's law, we know that EdA equals Q enclosed over epsilon. So for E to be 0, Q enclosed has to be 0, which means Q, which is on the black sphere, plus the unknown Q that is on the internal side of the shell has to equate to 0, meaning charge on B has to equal 0. Yeah, we called it B. So that means QB has to equal minus QA, which makes sigma B minus QA over the area of that sphere. Minus QA minus and QA is just Q, so this is minus Q over 4 pi, what's the radius for the sphere? A?
The inner one is A,
yeah. Yeah, so over A squared. So this would be sigma B. And if I were to move to the outer shell now, well, I know that there's no net charge on the green one. So that means I have a minus Q here. And if there's no net charge on the green one, that automatically means that the outer surface has to be plus Q, so that it would kill the charge. And so sigma at the outer one is C, so sigma C has to equal Q over 4 pi C squared. Yeah? That's the surface charge density on the outer sphere.
Yeah.
Questions on that? Okay, so we need to plot the electric fields, we have to find the electric fields. And the easiest way to do this is to use Gauss's law because we have symmetry. So we'll find the electric field in all three regions. So we have this guy and we have the shell. So let's go on a Gaussian surface first, where R is less than, what was the inner radius? A. R is less than A. So Q was sitting here, and if I take a Gaussian surface here with radius R, of course Q enclosed here equals 0. Gauss's law says EdA equals Q enclosed EdA equals Q enclosed over epsilon. As Q enclosed is 0, this tells me that for R less than A, E equals 0 on the inside Gaussian surface. Considering a Gaussian surface here. This was at radius R. Okay, now I'll go and I'll take another Gaussian surface. This is, so this is between the two. So let's go here. And this is R now. So for R, now between A and B, now Q enclosed is just Q, and Gauss's law is EdA equals Q enclosed over epsilon. Due to symmetry and E radially pointing outwards in the same direction as dA, this just becomes EA cosine 0, which is 1. So E times 4 pi R squared equals Q over epsilon. So E there, so that our second E is just Q over 4 pi R squared. So this is the second E, this is the first E, if we can label them. Okay, now we will go with a Gaussian surface between inside the shell, which is here. So now this will be R, and we know that this guy here is minus Q according to what we said. So when R is between B and C, between B and C, we know that Q enclosed is equal to Q minus Q total charge, which is equal to 0, which makes E equal 0 there. Clearly, it's a conductor, so it makes sense. Okay, and then the last part, when R is greater than C, when R is greater than C, so now I will take a Gaussian surface around the entire thing. So now this is my R, and clearly, and we said that the outer shell has a Q here, so that means Q enclosed will equal Q minus Q plus Q, which is Q. And so we will get EDA equals Gauss's law, Q enclosed over epsilon. So E times 4 pi r squared Q over epsilon, which makes E there Q over 4 pi r squared. And now that means if we do a sketch here, if we do a sketch, let's say that this is A, B, C, and here's the electric field. This is all in the radial direction, of course. If we do a sketch, we said that when R is less than A, E is 0. So E is 0 going here. Between A and B, it drops down as this was here. It drops down as an R squared, so it's like this. So it drops down as a hyperbola to be between B and C. Right at A, let's see, right at A, if R equals A, it becomes Q over 4 pi A squared. Okay, so that means it's somewhere here, let's say, and it drops down. And at B, it's going to be less, so let's say somewhere here. Okay, and between B and C, we said it's 0, so it goes down to 0. And then at C, it's back to 1 over RC squared, but the R, let me lift this up a little bit more here. So B is greater than A, so at B it has to be less than A, and C is greater than B because it's the outer radius, so it has to be the least on C. And so on C, let's say it's here, and it's going to go down like this. So this is a plot of the electric field, and now if I need the potential at 0, so I'll take my reference to be at infinity. So I know that V0 minus V infinity is equal, this guy here is 0 because I'm taking my reference to be at infinity, is equal to minus EdL from infinity down to 0. Okay, so in this case dl is just dr because the electric field is in the radial direction, so the displacements are in the radial direction, and we know that E also points in the radial direction. What's this? And so if E points in the radial direction, E is pointing in the radial direction, so and this is in the radial direction, so that means R dot R will just be 1. Okay, so with that said, now since we have different electric fields, we can separate the integral, so it will be minus from infinity down to C, and we take the electric field there. The electric field greater than C was Q over 4 pi R squared. So 1 over 4 pi epsilon Q over R squared dr minus, now I will go from C to B. C to B, between C and B, the electric field there was 0. It's a conductor, so this is 0 times dr minus, now I'll go from B to down to A. B then comes A. Let's see, B to A, between A and B, Q over 4 pi R squared was it minus or between A and B, Q between B and C, 0 outside, yeah, okay, now it's all plus. Okay, so this is Q 4 pi R squared dr, and now I will go from A to 0, and here this is a conductor. When we were less than A, the electric field was 0, so 0 dr. So clearly those two guys are off, equals 0, and what we have left here is minus, the integral of this is 1 over 4 pi epsilon. Let's get these guys outside their constants. Integral of 1 over R squared is minus 1 over R from infinity to C. Then the second one is 0, the third one is Q over 4 pi R squared, and this is same thing, minus 1 over R from A to B. The last one is 0, so evaluating this, we get Q over 4 pi epsilon. Let me cross out these minus signs here. So we get 1 over C minus 1 over infinity. This is 0. Q, oops, there is no R squared here. Pi epsilon. 4 pi epsilon. Let's make this a plus, and then this becomes 1 over B minus 1 over A. B to A, yeah. And if I factor out Q over 4 pi epsilon, I will get my final answer to be V. The potential at the center is Q over 4 pi epsilon 1 over C plus 1 over B minus 1 over A. This would be the final answer for the potential at C, for the potential at the center. Let me just check the signs really quick. Oh, 1 second here. By mistake, I switched the bounds. This is B, this is A. So we just flip the signs of these. So this is plus plus, so 1 over A. They're right up there, but here I just by mistake switched them. So 1 over A minus 1 over B, which makes this minus 1 over B plus 1 over A. Okay, there you go. So this is the potential at the center. Okay, so in part C, we ground the outer surface. If we ground the outer surface, that puts its potential at 0. So VC now will equal 0. Well, if that's the case, then there's no charge anymore on that surface. And sigma C goes to 0. And so how does that change the answers? Well, so now we have this shell, this sphere, and then we have the shell. This guy now is 0. This is still Q here. And this here will be minus Q to keep the electric field inside the conductor 0. And with that, so let's figure out the electric fields. The electric field, well, if R is greater than, so here what are the radii? We have A, B, C. A, B, and C. Okay, so if r is greater than c, q enclosed equals 0 and e equals 0. Okay, now if r uh, if r is in between um, b and c, if r is in between b and c, we've got uh, uh, 0. So e is 0. So here q enclosed equals 0. So that means e is 0 also. Okay, and now we're gonna go between, so this was C and B. Between, no, between B and C is 0. Now between B and A. So for R greater than A, less than B. Okay, here we do have an electric field because the Gaussian surface will have Q enclosed will be between A and B will be Q, and so the electric field will be EDA, so E, Gauss's law. I'll summarize since we've done it many times above. Q over epsilon, sorry, here, this is R squared. And so Q E will equal here Q over 4 pi epsilon R squared in the radial direction. Okay, and so this is 1, and then the last one, if R is less than A, this is certainly 0 because there is no, there is no Q inside. This is a metal. So E is 0. I should place this Q on the surface. Did I do that above? It's because the charge on the metal sits outside, just to be precise. Okay, so now this is E equals 0. So this is how the answers change. Basically, the outer shell is no longer charged, and so now V will also change. So V at 0 minus V at infinity. This guy is 0. And now if I go from infinity to C, the electric field here was 0 minus EDR, and then minus C to B, and here E is 0 as well, dr, minus B to A. Here I do have 1. E is 1 Q over 4 pi epsilon R squared R dr, and the last one, A to 0, here is 0. Okay, so they're all zeros except B to A, and so if I evaluate this integral there, we get Q over 4 pi epsilon R squared, there's a minus sign, and integral 1 over R squared dr from B to A, and V infinity is 0, so we get V0 equals Q over 4 pi epsilon. Oops, sorry, this r squared was inside the integral. Minus 1 over r from b to a. And so we get minus q 4 pi epsilon minus 1 over a minus 1 over b. And so the final answer would be v at 0 in this case. Flip the signs. 4 pi epsilon 1 over a minus 1 over b. So this is how the answers change, considering that we ground the outer shell. Oops. Okay, that does it for this question.